Welcome to the Explainer. Today we're diving straight into a fascinating, almost invisible world, the absolutely brilliant engineering that keeps modern railways safe. I mean, have you ever stood on a train platform watching thousands of tons of steel hurtling past you at crazy speeds and thought, how in the world does this not end in a massive disaster? Well, the answer isn't luck. It's a hidden, rigorous world of control systems and safety engineering. So let's just jump right into it.
So, here's a wild question for you. How do you build a system that is perfectly safe even when it inevitably fails? It's kind of the ultimate engineering paradox, right? Normally, we think of safety as just preventing failure. We slap heavy-duty cases on our phones so the screens won't crack, or we put massive deadbolts on our doors. But for railway engineers, failure isn't just a possibility. It's an absolute statistical certainty. Parts are going to break. Wires will short out. Software will inevitably have bugs. Because of that, ultimate safety isn't about stopping those failures from happening. It's about strictly, almost mathematically, controlling exactly what happens when things go wrong.
To see how they actually pull this off, here's our roadmap for this explainer. First, the philosophy of failure. Second, defining system integrity. Third, the software bug problem. Fourth, safety integrity levels explained. And finally, real-world railway applications.
All right, part one, the philosophy of failure. Understanding what goes wrong. You know, to a passenger stuck on a delayed train, every breakdown just feels totally random. But for engineers to build proper defenses, they actually have to strictly categorize these failures. And that brings us to a huge fundamental divide in design philosophies for both hardware and software. Random failures versus systematic failures. Let's think about the physical parts of the railway first. A relay switch wears down after a million clicks, or a cable degrades after years of freezing rain. Those are random failures. They're basically just the laws of physics doing their thing. And because they're physical, we can track them, build giant databases of reliability stats, and calculate almost exactly when a part is going to give out. We defend against this physical wear and tear using the classic fail-safe principle. So, if a part breaks, the system automatically defaults to a restrictive, safe state, like instantly turning all the signals to red. But systematic failures? Man, those are a whole different beast. These are caused by human errors in design, manufacturing slip-ups, or software bugs. They are baked into the system from day one, just hiding out in the shadows, waiting for the perfect storm of circumstances to trigger them. You absolutely cannot predict systematic failures using historical wear and tear data.
Section 2. Defining system integrity, beyond physical strength.
Okay, so how do engineers fight a war on two fronts, against predictable physical decay and completely unpredictable human error? Well, they use a highly formal framework. The key concept here is integrity. Integrity is formally defined as the likelihood of a system satisfactorily performing required safety functions under all stated conditions within a specific period. Now, what's incredibly interesting here is that phrase, safety functions. Because on the railway, a core safety function isn't just about keeping the trains moving on time. A vital safety function is actually the system's ability to revert to a safe state when things inevitably break. It's the system's ability to basically throw its hands up, stop the entire network, and protect human life the exact second a random or systematic error pops up.
Section 3. The software bug problem. The invisible threat.
So way back in the day, railways were controlled by purely mechanical and electrical systems. You could see the parts moving. But in the 1980s, the processor revolution hit, and it totally broke all the traditional safety models. Why? Because you just cannot fully test software in every single real-world scenario. Think of it like this. You can't microscopically test the absolute internal strength of every single weld on a massive steel bridge without actually destroying the bridge itself in the process. Software is similar. There are literally millions of combinations of inputs, timings, and environmental factors. And because we cannot mathematically calculate the probability of a systematic software failure occurring, our entire paradigm of safety had to shift. We can't just test the final product to guarantee it's safe anymore. Instead, we have to trust the rigorous competence of the engineers and the absolute strictness of the process they used to build it.
Section 4. Safety integrity levels explained. Measuring the unmeasurable.
So if we can't calculate the odds of a software bug hitting us out of nowhere, how on earth does the industry actually solve this? The answer is something called the Safety Integrity Level, or SIL framework. This provides a standardized way for specifying the required degree of confidence that an integrated system, meaning the hardware and the software combined, will actually meet its safety requirements. It's a tiered system. It ranges from SIL 0, which is just basic integrity, all the way up to SIL 4, which is very high integrity. And as you go up that ladder, the requirements get incredibly intense. To earn that top-tier SIL 4 rating,
Engineers have to use top-down design methods, strict modularity, highly verified component libraries, and just absolutely exhaustive verification and validation at every single step of the life cycle.
And here is the absolutely crucial point to take away from all this. Because the probability of systematic failure, like software bugs, cannot be calculated numerically, SIL relies entirely on the rigor and effectiveness of the design, verification, and validation methods used during development. We literally can't calculate the numeric probability of a bug, so instead, we mathematically enforce the strictness of the engineering process itself. If you use the most flawless, perfectly documented, exhaustively validated engineering methods known to human science, you earn that SIL4 rating. This guarantees that the likelihood of an unsafe failure slipping through the cracks is incredibly, almost unimaginably small.
Section 5. Real-world railway applications. SIL in action.
All right, enough of the theory and philosophy. Let's talk about where engineers actually deploy this incredibly demanding framework out on the tracks. The absolute beating heart of railway safety is something called an interlocking system. The interlocking handles the most critical signaling functions. It physically moves the track points so trains can switch tracks safely, and it clears the signals to give drivers the authority to actually move. Because this system is controlling heavy machinery and giving permission that literally dictates life or death, it absolutely mandates a SIL4 rating, the highest level possible. This safety layer sits right between the control center and the physical track. It guarantees that even if a human dispatcher makes a catastrophic mistake and tells two trains to enter the exact same track, the interlocking SIL4 logic will flat out reject the command and keep the signals stuck on red.
Now, you might be wondering, if SIL4 is so great, why isn't every single computer screen, mouse, and piece of wire in the whole railway network rated SIL4? Well, while interlockings demand SIL4, non-safety operator interfaces, like the computer monitors the signalers are staring at, usually only use SIL0 to SIL2. Why the difference? Because designing a system to meet SIL4 is mind-bogglingly complex, time-consuming, and crazy expensive. Plus, making something ultra-safe can sometimes actually make it a bit less reliable for day-to-day operations because it's just so hypersensitive to any little anomaly. So engineers have to be surgical about it. They isolate that maximum rigor strictly to the essential safety layers, the interlockings, while letting the display screens just be normal, highly reliable, non-safety critical computers.
So, we've seen how railways protect us. They anticipate failure, they isolate their critical systems, and they use insanely rigorous engineering processes to conquer the invisible threat of software bugs. But I want to leave you with one final, kind of wild thought. If the ultimate fail-safe engineering, literally the only proven way we know how to secure complex software, relies entirely on the absolute strictness of the human design process, well, how rigorous do you think the process was for the software running your car's anti-lock brakes, or your banking app, or the medical devices at your local hospital? The philosophy of railway integrity proves that true safety is never just an accident, it is a highly engineered reality. Thanks so much for joining me for this explainer, and definitely keep questioning the invisible systems running the world around you.